Hello, everyone. Today, we're going to be presenting our final project for ARO 3090 course with instructor Najuri. Our teams, we consist Joseph, Brooke, Justin, Safia, Brooke, and myself, Tony. Here's the outline of the project that we're doing. We will talk about technical analysis, and we will choose our final design. The mission overview, there are 10 mission requirements that we need to consider. And the most important ones are the entry velocity to Earth, as well as the it has to be no later than 2045. So why times? What times has been expected for life? Because this consists a lot of level of methane. We will use the methane to create fuels to get back to Earth, as well as to take the samples back to study. The modeling assumption, we will use these constants for Earth, Saturn, Sun, Titan, and Jupiter, and Venus in order to use these constants into our calculations.
We first considered doing the mission to Titan with a direct transfer from Earth to Saturn, which was also the same principle for the return trip. And all of that amounted to a total delta V of 53.9 kilometers per second. Slide, please. The heliocentric part of the mission was also designed in free fire, which confirmed the cost of a mission found earlier for impulsive maneuver. We also found the total time it takes to accomplish the transfer, which is 2197.9 days. Using Kepler's equation, we also found that departure time was 1.022 days and rendezvous time was 2.1 days. On the left, we have a small overview of the total mission. We're using the Vinci as our rocket engine, which has a specific impulse of 458.2, and we're using the SLS, which is capable of lifting 130,000 kilometers to LEO. However, our total launch mass was 171,000 kilograms, which is way too big for the SLS to be lifting, and that is the reason why we deemed the mission not feasible.
The Venus-Earth multi-flyby mission option. We used the Ames trajectory browser to generate porkchop plots for the best departure and arrival dates versus delta V for each leg of the mission. Since we used the Ames trajectory browser, this is going to be a ballistic mission. We know that gravity assists allow us to use a body's motion and gravity to redirect a spacecraft and then change its speed and direction. So we wanted to take advantage of that for this mission design. On the right is the trajectory optimization tool, which was used to verify and optimize the date ranges further. And in the center is a timeline of the overall mission, which I'll be going over in a later slide. So after the departure date and arrival date were determined, the time of flight was found, and then this information was entered into the Horizon System database in order to find the state vectors for Venus and Earth. So after that, this information was entered into Lambert's problem using MATLAB, and then the departure and arrival velocities were determined. And then using that information, the C3 of departure from Earth was calculated. On the right is a summary of equations for the Earth and Venus pre-flyby, as well as the Earth and Venus post-flyby and the Titan rendezvous. Next slide. So using the equation from the previous slide, the departure C3 was calculated to be 38.11 kilometers squared per second squared. This information was entered into the NASA KSC launch vehicle performance website, and the plot on the bottom shows the trade study that was conducted between the LS-5, the Vulcan, and the Falcon Heavy. After considering the ISPs and the payload capabilities of each launch vehicle, it was determined that the Falcon Heavy would be the best for this mission. The equations, sorry, please go back. The equations in the center were used to calculate the total mass of the structure as well as the fuel mass. The launch mass ended up being 49,500 kilograms. So here's an overview of the main mission legs and then a timeline of the major events for each part of the mission. So we're going to start at Earth and depart on May 24th, 2023. And then We'll do a flyby of Venus in September of 2023. Next is the flyby of Earth in May of 2024, and then we'll rendezvous with Titan in April of 2034. And then for the return leg, we'll leave from Titan in September of 2035, and then we'll return back to Earth with the sample in July of 2041. I have the delta V's and the time of flight for each stage of the mission below, but the overall mission cost and duration ended up being a total delta V of 62 kilometers per second and a total mission duration of 16.73 years.
For our third analysis, we chose to do a low thrust trajectory. This trajectory was based on one found through Ames, and we further optimized it through Malta. Our total spacecraft wet mass was 7,985 kilograms, with 6,738 kilograms of that being fuel. Our launch vehicle was determined to be Delta IV medium, providing just enough orbital capability and heliocentric injection for the mission. Our propulsion system for this mission was a 20 kilowatt nuclear electric propulsion engine with a duty cycle of 0.95 and 4,000 seconds of ISP. Our departure C3 was determined to be 37.85 kilometers squared per second squared, with a total delta V for the entire mission of 57.83 kilometers per second. This mission also utilizes a spiral into Titan orbit and out of Titan orbit, with a Jupiter flyby of 250,000 kilometers. Malta's accuracy was within 0.8 meters of a position mismatch. Next slide. In order to refine our trajectory in Malta, we developed a MATLAB script to generate pork chop plots for arrival and departure times as seen here. Next slide. So here you can see our timeline for the low thrust Jupiter flyby. We start on January 26, 2031 with the Earth departure with a V infinity of 6 kilometers per second. Our Jupiter flyby happens on the 15th of April, 2033, changing our V infinity to 6.45. Our Saturn spiral in begins on June 17th, 2039, ending at Titan's orbit arrival on the 10th of November, 2039. We spiral out of Titan's orbit on the 10th of May, 2040. This gives us a total of 182 days on Titan with plenty of time for sample recovery and fuel recovery. We exit Saturn's sphere of influence on the 8th of October, 2040, and arrive back at Earth on the 15th of November, 2045, with a V infinity of 0, giving us a free return trajectory.
After arriving at Titan, the plan is to leave the spacecraft in a parking orbit at an altitude of 1,000 kilometers. Then the lander will use a Hohmann transfer from the parking orbit to a periapse altitude of 350 kilometers. The lander, protected by a heat shield, will use the atmosphere and parachutes for the final landing. At the altitudes given and the periapse of 350 kilometers, we get a delta V of descent 0.0365 kilometers per second. Based on our assumptions for ascent, an atmospheric drag was ignored and the perigeo transfer ellipse was placed at the surface of Titan. The delta V for the ascent was calculated to be 1.5846 kilometers per second. Based on this delta V, the M10 rocket motor was chosen for ascent, allowing us to return 50 kilograms of sample.
On the bottom right, we have our CONOPS animation using Kerbal Space Program. Here we have our final design, trade study, and final trajectory selection with characteristics listed. As stated previously, we have an impulse direct transfer trajectory, but it was deemed infeasible as previously mentioned. We also have a Lambert transfer with a flyby at Venus and Earth with a delta V of 61.92 kilometers per second and a mission time of 16.73 years. We also had a low thrust trajectory with a Jupiter flyby with a delta V of 57.83 kilometers per second and a mission time of 14.8 years. Noted by the red and green indications, we have selected the low thrust trajectory for its feasibility, lower delta V, and lower mission time. The low thrust trajectory also has a departure C3 of 37.85 kilometers squared per second squared. It includes an atmospheric entry to Titan's surface and a Hohmann return to Titan's parking orbit. We also see, to reiterate, rocket fuel will be mined and processed on the surface of Titan. And our, once again, total delta V is 57.83 kilometers per second. Here we have our mission summary with a mission requirement completion verification table, illustrating how we successfully met our mission requirements. Thank you for your attention. This has been our Titan sample return mission presentation.